Hey students, I just got a great question about number 44. It's a very long one, and just the length of it can be intimidating, but it's got some neat parts. And so by the time we go through, wow, H, I, that's 9, J, 10, 11, 12. Okay, so 12 separate questions. We hopefully learn a lot about the difference between insulators and conductors and spheres. And so let's dive right into this. It says we have a solid insulating sphere of radius 5 centimeters that carries a net positive charge of 3 microcoulombs, uniformly distributed out through its volume, concentric with a sphere is a conducting spherical shell with an inner radius of 10 and outer radius of 15, it having a net charge of negative 1 microcoulombs as shown in the figure. So I printed the figure also here. And so coming back to the words here where it says, okay, an insulating sphere has a net charge. So in here, there's a net charge of 3 microcoulombs. And since it's insulating, the charges will stay wherever we put them, and so they can be spread out within the volume. And it says here, uniformly distributed throughout. So this brown sphere has a charge density of rho. And we'll talk about that in just a second. Okay. Uniformly distributed throughout its volume. Concentric with this is a conducting shell. And so this is is that kind of a bluish shell around it? Spherical shell has inner radius of 10 and outer radius of 15. Okay, so there's a little bit of a gap here because remember they said this was 5. So from the center out is 5, and then 10, and then 15. If I put distances, 15, 10, 5. Okay. And it has a net charge too. It has a net charge of negative. So maybe I'll put here negative 1 microcoulomb. So the whole thing has a positive charge of 2 microcoulombs. Okay. A. Consider a spherical Gaussian surface of radius 16. Now here's where the number is going to be important because where are we drawing this Gaussian surface? And at 16, it would be greater than the shell, the outer radius of the shell. 16 centimeters. And find the net charge enclosed by this surface. All right, well, I'll keep coming back to the picture here, but let's just start with A. And maybe coming here and saying, all right, on this first one, they're asking me to draw a Gaussian surface that is just 1 centimeter beyond the outer radius of the conducting shell. So in other words, this surface contains both the insulating sphere and the conducting shell. And so when it just says consider this Gaussian surface, find the net charge, we just have to add them all together. And so we've got a positive and a negative. And so this one, hopefully, is pretty straightforward in the sense that we're just going to come up with 2 microcoulombs of charge for the net charge enclosed. Now, you can imagine that that's part of Gauss's law. So we're going to go with that. Look at B. What is the direction of the electric field at point D to the right of the shell and at this radius of 16? Okay, so in the picture, here's point D. And so again, we're outside, and what direction is it? And this is my argument, and I'll use my typical red pen for looking for lines of symmetry. But if you draw a line through the middle, and you think about all this charge, and we really haven't got a chance yet to talk about how the charge is distributed on this shell, although that will come up. I hope you can kind of see that the charges move around because of their forces on them. They're in a conductor. And there wouldn't really be anything different along a line here versus a line here. And so I'll just draw maybe 3 lines of symmetry. And however the charges distribute themselves, I would think it'd be kind of the same up here as down here, or the same to the left as to the right. There is no directional preference, left or right, or up or down, or in this case it's 3-dimensional, so forward or back. But we would then be able to argue that because they're evenly distributed, you take this whole thing and flip it, you get the same charge distribution. And that means whatever electric field you have, which we've been doing electric field in kind of this burnt orange color, something like this would be an impossible electric field, because when you flip it, this electric field would now point in this direction, which is different than before. And the reason that can't be possible is because once we flip it, we have the same charge distribution. So how could the same charge distribution now create a field that's in a slightly different direction? Well, it couldn't. And so that's our symmetry argument, that this field would not be appropriate. And I'll say it again, because when you flip it, the charge distribution is the same, yet the direction of the field is different, and that's an indirect reasoning that, hey, that just can't happen. And in fact, then, the reason we like lines of symmetry is because lines of symmetry then are also the direction of the electric field, because the direction along the electric field is the only direction you can have where when you flip it, ending up with the same symmetry, that's why it's a line of symmetry, for the charges, you must get the same direction of the electric field. And so we know by a symmetry argument that the electric field must be along these lines of symmetry. And the lines of symmetry are radially outward. And so in this area, we would have radially outward. And that would also really be true anywhere. As we dig deeper into this problem, we might be asked for the electric field in this open space, or even in this insulator, or even in this conductor. And we know this, that they will be radial, because those are all lines of symmetry. So they haven't asked that much yet. That's okay. But what I could put then is maybe just this word, that these are going to be radially outward. And again, it's a symmetry argument. Okay, moving on then to C, it says find the magnitude of the electric field at this point D. Okay, so they are asking us really to continue with our first 2 steps, and really they're saying do a Gauss's law, because when you do a Gauss's law calculation, these would be your first 2 steps. The first one being how much charge is enclosed by the surface, and the second one is look for symmetries so you can make, well, the next step argument. And I will do that, but let me go back to A and say, okay, how much charge is enclosed? Well, it's 2 microcoulombs, okay? And then this side, when you do the dot product, you can argue that that angle is 0 degrees. That's where the symmetry argument comes to be into play here, because you want to be able to say what is the direction of the electric field compared to the normal vector. Now, the normal vector we normally do in black, and so looking maybe right here, we already said that the electric field is radially outward, but also looking at a surface, and the normal vector is perpendicular to it, and so I'll draw it in black. But if you'll hopefully notice as I go around my Gaussian surface here, the direction of my normal vector and the direction of the electric field are all each radial. And so everywhere along this Gaussian surface, the angle is 0. And so that's what I mean by we have to do these 2 steps, especially this step in B, to get at the direction before we can do this integration. Because also part of the symmetry argument is that, okay, not only does it give me the direction of the electric field, but it lets me figure out something in reasonable fashion about the magnitude of the electric field. Now, the magnitude of the electric field, let's come back to our picture. If you imagine kind of you standing on this and kind of looking back at the distribution of charge, you would say, okay, the charge is made from that charge distribution. And if you imagine standing somewhere else, like here, you kind of look back and you see that same charge distribution, which is why you would say then the electric field is not only radially outward like it was here, but also the same magnitude. And that is going to be our important step here, because we are going to then say that we can pull the electric field from inside of the integral outside. So even though we don't know exactly what its equation is, we make that argument that it's a constant. And I want to be careful with this phrase. It's constant on the Gaussian surface. So I'm not saying it's a constant as you moved further out or back in. So there can be some variations with that electric field. But along the Gaussian surface, the part I'm asked to do the integral and add up on the surface, it is a constant. And so you'll see when we're all done, we'll get the electric field. And we won't say it's a constant. We will say it does vary as you go in and out radially. But we will say that for a given radius, it is a constant. And that's what we're asked to do, the integral on a Gaussian surface. And I suppose I should have kept my little symbol for the closed surface. All right. And that makes the math pretty easy, because then doing an integral of a surface, and this is a spherical surface, we can just put the equation for the surface area. We don't have to actually do the integration. We can just kind of read the math and say, well, this says you add up all the little areas on the surface, you're going to get the total area of the surface. And since it's a sphere, it'll be 4 pi r squared. So finally getting to the electric field, I can put my 4 pi and epsilon naught together, and I can put my charge, which now I'll write as 10 to the minus 6, and divide it by r squared, and that'd be coulombs. And I think we could even do a little better and get a number. Let me come back to the question. I think they wanted more than the formula. I think they wanted an actual number. Yeah, find the magnitude of the electric field at point D. And so remember, point D is 16 centimeters out from the center. Okay. So I can put in a 4 pi, and then this would be the 8.85 times 10 to the minus 12 here. And maybe I'll put my units over here. This would be Newton meters squared over coulombs squared. Okay. This is this 2 micro, and so I'll put the coulombs with it. And then the distance is the 0.16 squared, and that's meters squared. And so in terms of units go, the meters squared is going to cancel off, and one of the coulombs leaving me with newtons per coulomb. All right, so why don't I do maybe this lower part? I could probably even save myself some calculating work, realizing that is Coulomb's constant. So I'll just put in Coulomb's constant. Remember, Coulomb's constant is made up of these two other constants, one with the material, free space, and the other with the geometry. And then this would be 2 times 10 to the minus 6. And then this is 0.16 squared. And it looks like we are 7.03 times 10 to the 5th newtons per coulomb. And so there is C. And maybe I should start numbering these pages because this is going to be a long problem. We've done 3 of the, 12 parts because we go down to letter L. Okay, so going on to D, it says find the vector electric field at the point C, which is at a radius of 12 centimeters. All right, so now we get into something a little bit different. C is actually inside the conductor itself. And we're going to take advantage of an argument we did with Gauss's law and say that the electric field has to be zero inside a conductor. At least it has to be zero at steady state. In other words, the argument is another indirect argument, like our line of symmetry arguments. We would say, well, what if it's not? What if there was an electric field inside a conductor? Well, that means the electric field would supply a push on the charges that are in the conductor. And that means the charges now would shuffle around, changing the field. And so when would they stop shuffling around? Well, when they have no more force, which is when they have no more electric field. And so conductors are kind of nice in the sense that the charges shuffle around. So eventually you end up with a field of zero. Now, you might not have it for a while until they get done shuffling around. That does take some time. Usually it's 10, 20 nanoseconds, maybe as much as a whole microsecond. But it's still a very, very short period of time, and that's kind of my argument here. And I think that's what they want. We're doing electrostatics. We're not worrying about them shuffling around. We'll worry about charges in motion real soon, but this is just the start of the semester. So there's our argument here, and so we're going to get anywhere inside of there. So anywhere from 10 centimeters to 15 centimeters, the electric field should be zero. Now outside, and maybe we should have made a comment here back in part C where we calculated the electric field outside of both spheres. We got this equation and then we applied it at a distance of 16. But I'm hoping you see that this right here could be extended to, say, 17. Because we would kind of mentally just do everything we just did. We would just draw a Gaussian surface with a bigger radius and we'd come up with exactly the same equation. Or we could go at 18. And so in other words, this would be a valid equation for any radius, as long as we're outside. That was part of this argument that, hey, what's the total charge? So anything greater than 15, in fact, maybe I should put, R greater than 0.15 meters, this would be true, whereas this would be true when R is greater than 10 centimeters and less than 15. Okay? And so there is, I guess, 2 of the 4 regions we are going to be asked to find the electric field in all of this. All right, that gives us a chance to go on to part E here. Now considering a Gaussian surface through the point C and find the net charge enclosed by this surface. Okay, so let me go ahead and maybe just write out Gauss's law. And maybe I will also draw, although this picture is going to get pretty busy before this problem's over. But if I were to draw a Gaussian surface at 12, and I'll even extend that to say anywhere between 10 and 15, you are going to get an entire Gaussian surface that is enclosed entirely with inside of the metal conductor. And because of that, the electric field is 0. And so if you do an integral over this field, which is 0, you're going to get just 0. And the reason that can be helpful is this is saying that the total charge inside would be 0. And that is what E is all about. Consider a spherical Gaussian surface through the point C and the net charge enclosed by the surface. All right, well, moving on to the next page, page 2, question F. And F says, consider a spherical Gaussian surface of radius 8. Oh, I thought they were going to ask more about this one. Oh, kind of disappointed. Well, maybe they will later on. Okay. So we'll come back to that. But consider a spherical Gaussian surface at radius 8. So 8 in my picture would be somewhere around here, point B. And find the net charge enclosed in this surface. Well, again, just kind of looking at the picture, kind of like we did in A, we said this was the smaller sphere and then this was the metal shell. We just now would not have the metal shell, so we would only have the 3. And so it's just 3 microcoulombs. Okay, let's go on to G. Find the vector electric field at point B. Okay. Now they say vector field. Didn't we do one like this in our symmetry arguments? Yeah. And it just got me thinking that maybe in part C, what did it say? Oh, so it just said find the magnitude. And then D, find the vector field at point C. Okay. Yeah, I was just commenting that I didn't do a direction here, but I think I'm okay because I didn't really ask for it in C. They just said find the magnitude. But see, I noticed something a little different here in G. They say find the vector field. So they want the magnitude and direction. And I thought they had asked for it somewhere else, but I guess it was D. But we didn't have to give a direction in D because it's just 0. And 0 doesn't have a direction. It makes no sense to say we have 0 direction or 0 steps in the X direction or Y direction. Okay, but G says find the vector. So we need direction as well as magnitude of the electric field at point B at the radius of 8. And so, again, this is kind of like the one we did for C, part C, where we're going to put the charge inside and we're going to do some symmetry arguments. So the charge inside is the 3 microcoulombs over epsilon naught. That's why we did F. And then taking the dot product and doing our same symmetry arguments. If we're looking at a point inside, we still have these same lines of symmetry on the inside. And so we're going to say the angle is 0 everywhere along this Gaussian surface that is inside here at 8 centimeters from the center. And we're also going to make that same argument that the electric field would be a constant over that Gaussian surface. And again, we do that part of the argument by saying imagine yourself standing anywhere on this Gaussian surface. And as you look back to the charges, they look symmetric. And in this case, you might look into the center, they look symmetric, but you also might look out behind you, but again, they're symmetric. And so you're going to get this symmetry lines radially outward. And if you compare yourself standing here to here, you're going to see the same thing. You're going to look inward. And so here you look inward, you see the same charge distribution. And here, if you look outward, you kind of see these charges, but they would look the same as over here. And so whatever that magnitude is, which we're asked to solve for it, it would be a constant on that surface, so we pull it out. And then this is just the area of that surface, which in this case is a sphere again. So it's 4 pi r squared. And so everything I'm doing really is exactly the same thing I did on page 1 here. It's just my r isn't valid, or my argument is, for things greater than 15 need to be done here. This would be an argument when r is greater than the 5 centimeters and less than the 10 centimeters, meters. meters. But interestingly enough, I get the same kind of equation. And it makes sense because everything comes out to be exactly the same. But the big difference is the charge inside is different. And here we have 3 microcoulombs inside. Whereas back when we did part E or C, we got the total charge inside, which was the 2 microcoulombs. So again, reminding myself that this is Coulomb's constant, so 9 times 10 to the 9th Newton meters squared over Coulomb squared. I can change this to 3 times 10 to the minus 6 coulombs. And this, oh, I'm sorry, didn't mean to write that. I meant to write r squared there. So there's my epsilon naught, and then there's my r squared. And I can now put in my radius in squared. And I'm pretty sure it was 8. I've been talking so much I kind of forgot where I find the electric field vector at point B at a radius of 8 centimeters. Yeah. And so now I can actually do a calculation. And it looks a lot like the last one. So maybe to save a little bit of time, I'll just hit re-enter. Because there's Coulomb's constant, and instead of having a 2, I have a 3 times 10 to the minus 6th. And instead of having a 16, I have an 8 squared. And so this is going to come out to be 4.22 times 10 to the 1, 2, 3, 4, 5, 6. And looking at the units here, it looks like meters squared will cancel off and one of the coulombs. And so we'll have newtons per coulomb. And let me be careful here, since it did say it was a vector, it would be radially outward. Now, if you wanted to say, well, at point B, radially outward then is to the right, I think that would work also, because they're saying, you know, what is it at point B? But I like radially outward as a better description because it's radially outward, you know, anywhere along that surface. So if I was looking at this part, it'd be up, and if I was looking at this part, it'd be left, and I was looking at this part, it'd be down. All right, well, continuing on, let's go to part H here. H. Consider a spherical Gaussian surface through point A, which is at a radius of 4 centimeters, and find the net charge enclosed. I think this might be a little bit of a harder one, because point A, being right in here, does enclose a percentage of the total 3 microcoulombs, but not the whole thing. So this might be a little bit harder, but we're going to need it to do Gauss's law, and that's why they're saying here, okay, consider a spherical shell, find the net charge enclosed. So you might do something like this. You might say the charge is what you get when you add up a bunch of little charges. So if you come back to our picture, you'd say, let's add up a bunch of little charges in here. But we're not going to go all the way out to 5 centimeters. We're only going to go part way out. And this is where that concept of charge density can be very powerful. And we've done problems that have charge density along a line and charge density on a surface. For a line, we tend to use the symbol lambda. For a surface, it's sigma. And for a volume, it's rho. So for this problem, I'm going to use rho. And you could think of rho in 2 different ways, especially, and if it's uniform. You can always think of rho, uniform or not, as some kind of small charge. within some kind of small volume. But if it's uniform, and only if it's uniform, you could also think of it as the whole charge spread out through the whole volume. And I will do that eventually. But right now, I'll just think about a small amount of charge. And here's how I'm going to think about it. Maybe I'll take small paper here. And I'm going to think of this little ball of charge inside of A as made. I probably can't do a good job of folding this to make a sphere. Do I have anything I can fold it on? Yeah. Maybe I'll try this. Okay, so let's see. Maybe I'll get a little bigger piece of paper here. But if you imagine folding this all the way around, I would have a spherical shell. And if you think about doing that multiple times, you could start with a really small shell and keep adding it bigger to get a solid piece. And so the mental picture I'm trying to get you to see here is I'm going to say that I have one shell, plus another shell, plus another shell. And I'll eventually get a sphere. Okay. So when I say a small amount of charge, I'm going to say something like this, a dq, and I'll just put on a shell. And so this is a spherical shell, which means then I have to have the corresponding volume, and I know my paper didn't wrap all the way around. But if I had this shell that wraps all the way around, and so here's my shell, and I unfolded it, you would say it's volume. Okay, so right here, the small amount of volume is this surface area times this thickness of the piece of paper. And it's really, really thin. It's infinitesimally thin. And the surface area is the surface area of a sphere. So I'm going to say it would be 4 pi r squared, where r squared would keep changing as my radius got bigger and bigger. Okay. But one shell would have a certain radius, and then that 4 pi r squared would be its surface area. So again, each shell would have a little bigger surface area. But I would say that each shell has kind of the same thickness to it, and that I might use a little bit of calculus and say it's a thickness of dr. And this is how I'm going to answer part H and say, okay, the charge enclosed then would be this little bit of charge on a shell added up. Okay, and so that little charge added up would be, actually maybe I'll write it in 2 steps, dq of a shell. And then I can replace the charge on a shell with 4 pi r squared times rho times dr. That's what I get when I substitute that in. And the reason that can be very useful is I could then literally add up, starting with an r of 0 and increasing to wherever it is I need to stop. And let's see, going to this problem, H, it says add up until you get to a radius of 4 centimeters. Okay. Now, maybe for starters here, I will call this, and hopefully it won't confuse you. Let's see, I've been calling little r the radius of each shell. So why don't I add up until I get to some radius? Can I just call it like an r prime? So I'm going to go from 0 to r prime. And I'll take the 4 pi out in front, and there's a magical step. The density, the charge density is a constant. I can pull that in front. Because then I have just an integral of r squared dr, which becomes r cubed over 3, and I'm going to add them up from 0 to r prime. All right, let me go to another sheet of paper here. Still continuing on H. So this Q then would be 4 pi rho. And then I'm going to get an r primed cubed over 3 and then minus 0. So let me not bother to write that. And then if we go back to what we said earlier, that you can think of rho as the whole charge over the whole volume, I can then replace this with the whole charge. So 3 times 10 to the minus 6 coulombs. And I guess I better be careful with the word whole. I'm talking about just the insulator hole. So if I went all the way out to the edge of the insulator, not this whole problem hole, but just to here, you know, as it said, it's the whole charge is 3 microcoulombs. Okay. And if I divide by the whole volume, the volume of that sphere is 4/3 pi, and it would be r cubed. And the r was that 5 centimeters that we wrote right here, and that they listed right here, radius of 5 centimeters. So that is the density. And then, of course, right here, our limit of our integration was the 4 centimeters, right? Because they said consider spherical charge, you know, radius 4, find the net charge up to radius 4. So this would be 0.04 cubed over 3. Okay. And it looks like I can save myself a little bit of calculator work if I cancel off the 4 pi's and I take that 3 and move it up to here. So across the top, I have 3 microcoulombs, and then I have 0.04 raised to a power of 3. And I have time. Oh, actually, looks like I can save myself a little bit of calculator work and do that. So then I will do divide by 0.05 raised to a power of 3 and hit enter. And so I told you this was going to be a long one, and it's 1.54 times 10 to the minus 6 coulombs. So it's about half the total charge. Remember, the total charge on this sphere is 3, and so we're about halfway there. We're at 1.5. Even though our radius is way more than halfway, right? Because the volume is pretty small in here. Most of the charge is out on the last part of it, because the last part of it, as we stack the shells together, the last shells take up most of the volume. And so it's just kind of the last part of it. Okay, so let's keep going here. Like I said, big problem. Let's go to I. So I says determine the charge on the inner surface of the conducting shell. Now this is a fun one. Let's put some things together here, because what we said back when we were trying to get the electric field at point C, which I think was problem D right here, we said it was 0. And so that means the charge enclosed would be 0, and that was E. So maybe a new picture is worth drawing. So if I have the insulating sphere in here and the conducting shell, because of what we just did in steps D and E, if I draw a Gaussian surface anywhere in here, I get 0 for the flux because of 0 of the field, which means charged inside is 0. And that would be true even though they asked me to do it at point C, which was at 12 centimeters. I could argue that that same Gaussian surface brought all the way up to the inner edge at just a hair greater than 10 centimeters would come up with the same thing. And this inner part has 3 microcoulombs of charge. And then because of that, you know what? I just realized that I read J, didn't I? Okay, let me keep going and come back to I. So J says determine the charge on the inner surface. All right, so keep going with my argument. I'm trying to say here that if you have 3 microcoulombs on this inner sphere, but the net charge has to be 0 when you just go just inside of that inner surface, there must be then a bunch of negatives on this inner surface. And so that inner surface must have a charge of negative 3 microcoulombs. And we're going to use that argument. In fact, that reminds me of a video I did much shorter than this. I believe it was number, let me see if I can look at the problem. Was it 39? Yeah, 39 looks like it. That's what and so we did one of these arguments in 39. 39 was a much shorter problem, but this part was the same, about how much charge was on an inner surface. And so we had to come up with the negative 3 microcoulombs there. Well, sorry about skipping over I. It would be more logical in order here. But I says then find the electric field vector at point A. And so if I do the Gauss's law, E dA charge inside epsilon naught, you can see then why they had us do H here and find that total charge inside, 1.54 times 10 to the minus 6 coulombs. And maybe I'll just put the epsilon naught here and come back to it in just a second. But again, like we did in the other ones, and so let me just kind of do this a little quicker. We could argue that from the dot product, we get cosine of 0 degrees, we get a dA, and we get an electric field that is constant along that surface. And so the electric field replacing this with the 4 pi and then r squared. So 4 pi r squared, I'll just move to the other side, the epsilon naught, and then this charge of 1.54 times 10 to the minus 6 coulombs. And so then I can do the 9 times 10 to the 9th here. I can do the 1.54 times 10 to the minus 6. And I can do a radius of, and I probably should go back and check. We were at point A, and point A was, consider point A, then find this field at point A. Okay, and so this would be the magnitude. And it too would be radially outward when we get into the part that says what is the direction. And so 9 times 10 to the 9th times 1.54 times 10 to the negative 6 divided by 0.04 squared. And so this would be 1, 2, 3, 4, 5, 6. So 8.66 times 10 to the 6. Let me just check that. 1, 2, 3, 4, 5, 6. And then when I put in my units, like some of the earlier ones, we get newtons per coulomb. Okay? So there's I. And then there's J. And so moving on to page 4. Let's talk about parts K. Okay, K says what? Determine the charge on the outer surface of the conducting shell. Okay, now maybe it's worth repeating the argument that I started 46 minutes ago when I said when you draw a Gaussian surface, or what is the electric field inside a conductor, it is 0. Okay, and we've used that many, many times here. And now we're beginning to see a little bit more of the physics why, because what we've concluded so far is that if there's a negative 3 microcoulombs on the inner piece, it makes an electric field in fact, there's electric field inside because this is not a conductor. And I think that'll be the grand finale. But when it hits this conducting surface, it's got to terminate the electric field. That's why there is negatives that get pulled inward. And enough negatives get pulled inward, which is exactly equal to these, to get us a negative 3 microcoulombs on that inner surface. That was the conclusion we got from part J, where we said, okay, there's a negative 3. And that terminates the electric field. But of course, where did they come from? They came from this metal. And there, like I said, there has to be a negative 3. There has to be just enough negative charges to terminate that so there'd be no field coming into this area. And so that's why the negative 3 comes in here. And so we know there's a negative 3. And that negative 3 would have come in and then have left a positive 3 on the outside if the shell was neutral. But remember, we said, and this was way back in the very first step here, that the total charge of everything was 2. So that would mean that if you drew a big surface around it, like we did back in A, which encloses this negative 3 and this surface negative 3, this outer surface must have a plus 2 on it. And that makes total sense when you look at the shell itself, because now the shell itself, if you take the outer surface with a plus 2 and its inner surface with a minus 3, the whole thing on here is a negative 1. And that's how they described the problem when we started, that the whole thing would have a negative 1. We just had to do some argument of how it was distributed. And so our argument kind of concludes right here that, okay, it may have a total of -1, and here's how it is distributed. -3 move over to the inside surface, no net charge in this area, otherwise there'd be an electric field and things would shove around until it wasn't. And so the only left option for the charge to be is on this outside surface. And that's kind of the extension, if you remember when I was saying why, if we draw a Gaussian surface and we draw it just real close to this inner surface, there would be 0 field. We can do the same thing if we draw to the outer edge. There would be no electric field, and so the flux would be 0 and the charge would be 0. And so that means if you already drew a Gaussian surface here and the net charge is 0, you draw another one and another one and another one, and you keep drawing it all the way until you're microscopically shy of 15, you would still not have a net charge, and then therefore are a field, and so therefore you would not have a net charge. Therefore, none of the charge is there. The charge must be just on this boundary as you cross back out. And so to make the total charge come out to be a +2, we have to have the -3 here, a +3 on the inner ball, a -3 on the inside surface of the conductor, and then a +2 on the outside. All right, so there's K. And then finally, if we put all this together, I think they're asking for a graph. Yeah, sketch a graph of this magnitude of the electric field versus R. Okay, so I draw the electric field as a function of R. From 0 to 5, it would be inside of this insulator. From 5 to 10, it would be in this kind of this inner space. From 10 to 15, it would be inside of the metal conducting shell. And then beyond 15, it would be what we did first with D. Okay. Now, we talked about outside moving in. We didn't do a real good job of talking about the field on the inside. So I think to finish this, we got to talk a little bit more about what we did to get the field at point A, which was on page 3 somewhere. Well, here it is. And we did that by getting the amount of charge inside. See, and we said the amount of charge on the inside was related to this R prime, which we eventually set equal to 0.04. But if we were at some other distance, like 0.03 or 0.02, the logic would still be the same. It would just be a smaller number. So what makes that important here, and I didn't really write it this way when we calculated the field, which I guess was I. We just kind of threw it in. But if you'll notice, when we did the surface area, we had an R squared, and that was of the Gaussian surface. So that was really a prime there, which would have canceled with this R prime, or at least 2 of them would have canceled. In other words, it would have looked a little better had I done this math. This side of the equation I could write as E times 4 pi R prime squared. And on this side of the equation, I'll just first do 1 over epsilon naught. But the charge inside would have been this 4 pi charge density rho R prime cubed over 3. So that the 4 pi's would cancel off. And this is the part I was saying, the r prime squared would cancel with 2 of them, leaving just 1. And so if we left it in terms of an equation, we would have the density of that charge times r prime over 3 epsilon naught. And that's really enough to show then that the electric field would increase according to the size of the Gaussian surface we draw. And of course, like I said, when we actually did it, we were asked to draw it at 0.04. Yeah, right here. See, right here, 0.04. But this would work if it was 0.03 and 0.02, or even a 0. And so this equation is saying the electric field is linear with the radius on the inside. So when r equals 0, the field equals 0, and it grows linear while we're inside. I suppose you could even do this step, which, remember, was the total charge inside divided by the total volume. And let me represent the total radius as a capital R cubed. But I want to do something a little different than the little r or the little r prime so that you can see that this r, which is coming from the charge density, is not really the same as the radius of the Gaussian surface. And it's also not the same as the radius of each individual shell I'm building up that eventually makes the r prime. And so there's an r prime, and a capital R in this problem, and those can easily get confused. So that's the hard one. Now, the others, I think, are pretty easy. We actually did this one somewhere. That would be in the area of B. What question was that? B, I think, was page 2. Yeah, right here. And we got this r squared effect as we moved out from 5 to 10. And of course, you can kind of see that when r is equal to 0.05, it would match up with this equation. And so it would begin to taper down until we got to this shell. And so here, the field would be proportional to r, whereas here, the field would be proportional to 1 over r squared. And then, when we get into the shell, there's just like instant drop, or nearly instant drop. There would be some kind of boundary layer. But that's where these charges were, and so it would drop down to 0 inside the conductor. And that 0 field is what we solved for back on page 1, in part D, where it says what is that electric field between 10 and 15 centimeters. Okay. And then finally, what we did was on the outside, which I think we did very first. So they tried to give us the easy working in instead of the kind of the way you might think about it, the harder one, and then working out. But we've got this equation, which again is proportional to 1 over r squared, and it's valid for greater than 15. And it would match up, actually, to, well, no, it's not going to match up because the total charge changed. Okay. And so let me just do a dotted line. If we didn't have this shell, it would have continued on. And it still kind of follows a 1 over r squared pattern, but because this has a net charge of -1, it kind of takes away from this by a value of 2. And so it wouldn't be quite as high, and then it would follow a 1 over r squared value. because the total charge does change, right? In this area here, which your author called C, the inside charge is 3 microcoulombs, but here in area D, it's 2 microcoulombs. And so this would be falling off at also at a 1 over r squared value. All right, well, that was a long problem, so hopefully you made it all the way through. Congratulations if you did. Hopefully you took some breaks in between. But if all of those steps made sense, then I think you got a good grasp of this chapter and you're ready to move on to the next chapter. All right, take care.